Hello, we are the Oracle-sponsored team for EMC hardware and software. My name is Sergey Protetsky.
Kevin Jesse.
Travis Johnson.
James Jokini.
John Dilger. Hunter Nichols.
And Sean Zadaport.
So the motivation for creating a EMC controller and hardware and a software driver were that Oracle was looking into possible non-volatile memory options, and EMC was a potential alternative. Motivation for creating a hardware host controller were that we were allowed to customize our interface with the EMC device through the FPGA fabric of the Zynq system on chip. The Zynq consists of two ARM 32-bit Cortex A9 processors. So we were able to develop a software driver to accompany the hardware host controller, and thereby allowing for hardware-software co-design and allowing us to effectively communicate with the UNC device.
We had 4 project goals. First, we wanted to create a hardware controller that could translate requests and responses to and from EMC memory. To interface with that controller, we wanted to create a software driver that would send and receive those requests and responses, and also manage the EMC state and error conditions. We wanted to combine those to create a robust system, and finally wanted to achieve the highest performance possible with our EMC device. And that means running the bus at 52 megahertz, using double data rate, which means that we send and receive data on both the rising edge of the clock and the falling edge of the clock, and finally using the full bus width of EMC, which is 8 bits wide.
We use an AXI interconnect for data transfers between our software driver and hardware controller. AXI is a specification published by ARM to facilitate communication between their processors and programmable hardware. In our initial design, the hardware controller did most of the work, while the software driver would just send addresses that it wanted to read from or write to the hardware controller and wait for a signal to let it know that it was ready for the data transfer, which it would then complete. We moved most of this work to the software driver, which made it more flexible, more scalable, and then we could have more chips and more reliable overall.
In the hardware implementation, we receive a command and argument from software and translate it to the eMMC specification to send to the device. The device then responds, which we return to software. If the command is a read or a write, we then complete the data transfer. For example, here is a write command. We have the command and the response, followed by the controller sending data to the device and the data responding.
Our controller's other functionality is to detect errors and inform the software driver that they occurred. Our controller detects 2 types of errors. The first is if the EMC does not respond to our controller within a specified amount of time. This can occur if the EMC does not send a response to our command or does not send data to our read command. The second type of error that our controller detects is if on the response or the data that we receive from the EMC, it's corrupted during transmission. Our controller also implements a set of custom commands that allow for the software driver to set functionality within the controller. One of these commands is to set the clock speed between a high and low frequency. This is important because the EMC requires a low frequency during its initialization, but it can be difficult for the controller to determine when to set this. Therefore, we give control to the software driver through the custom commands.
One of the implementation challenges that we faced was a clocking issue. So the EMC memory receives its clock from our hardware controller. Now, if we simply sent out our internal clock out to the EMC device, we would end up with the situation up top here. You can see we send out the clock and the data. You can take note that we are, again, running a double data rate mode, which means that we are sending and receiving data on both the rising edge and on the falling edge. Now, the problem with this is that the clock, the clock that's internal on the controller is very precisely timed. And when we send it out, small variations in latency caused by heat and trace length will cause it so that when the EMC device attempts to capture data using this clock, it will violate hold times or setup times. Basically, it will try to capture data as the data is changing, causing inconsistency. Our solution to this was to send to the EMC device a 90-degree shifted clock, allowing us to capture the data when it's nice and stable and not violate any hold or setup times.
The software driver is a mediator between the user and the aforementioned hardware. In order to provide the user with a smaller and more sophisticated set of requests that you would expect from a generic type of memory device. We break down the user's request into a series of command response pairs. In the diagram, the user's request in blue, which could be a read, write, or initialization process, triggers us to send command A. In command A, we start sending the command into hardware where it'll be processed by them. Next, we wait at response A for the return from that hardware that will confirm to us that we have continued in that eMMC process. We'll go down the line, and not pictured is, say, command B and command C and others, but we will continue doing the same thing until we reach success and return that to the user. In the event that errors occur, we will have a different flow. Here, after response, we see that at our success, we diverge and go into this repair state. At this point, we attempt to discover where the eMMC device itself, the hardware, had gone rogue, and attempt to identify the solution to this. The solution will be a sub-series of these command response pairs. In this case, it's just one of the command response pairs, but it doesn't necessarily need to be the case for that. In this event, we retry the command A and response A in the event of that communication error. And if the communication error becomes resolved, we can continue to success despite the error occurring and prevent the user from being burdened by this. In order to do this, we need to have a model for the eMMC chip in software.
This model is achieved with the state transition model. What this allows us to do is to facilitate the issues that occur from the eMMC device. What we do right now is we autonomously will send the next command in the sequence to achieve whatever the user's request is. So say we're doing initialization, we would want to issue commands A, B, C, and D in the order that completes the initialization or the user's request. Since we now have to consider error handling, which occurs naturally in initialization due to the lack of the response from the chip, we need to reissue a command 1 several times before issuing the command 2 and 3. When the command 1 is successful, we can move on. If the command fails, we remember the state that we're in and the task that we're trying to accomplish and either reissue that subset of commands or the entire task that the user asked for. In this case, it'd be initialization. There are a lot of benefits with this type of model. We always will have the optimal sequence necessary to complete the transaction, and we also have reliability between the commands and the reliability of the reads and writes. When we have reliability of the reads and writes, we can make sure that we have data reliability in the sense that if a partial read fails, we can reissue the read on a subset of data and return the complete response back to the user. This is not seen by the user and is abstracted away from them. This is because it makes it clean, and the user will only see the returned result back and not realize that there is maybe any issues regarding the communication between the hardware controller and the eMMC device.
We received an eMMC 4.41 device for testing, and we were able to implement all supported data modes on this device. We got speeds of about 20 megabytes per second on reads, and an average of about 4 megabytes per second on writes, but with bursts up to 22 megabytes per second. The main limitation on speed is the busy period after a write during which the device is programming, and the time it takes for the device to return data during a read. Our controller is able to match the speed of the device.
And our results confirmed that the software driver was a successful mediator between the hardware and the eMMC logic.
So the software driver results is that we want to make sure that we achieve every functionality and took advantage of all the implementation success that the hardware controller has implemented. This takes full advantage of the hardware controller. We were able to achieve maximum full bus width as well as the dual data rate. We were also able to achieve basic driver functionality, which includes initialization, read, write, block reads and writes, and also putting the chip in an inactive state for safe power off. We were also able to co-design this with the hardware team and implement several features that you can only do well in software. It is very difficult to implement these extra features in a hardware controller because it's much more complex and takes a lot longer time to synthesize and test in hardware. Some of these features were data reliability on the reads and writes, as well as querying the chip to see how big it is. In this case, we were working with an 8 gigabyte chip, so we return the maximum sector address back to the user and make sure that a read or write doesn't violate that space. We're also able to add in features like unlimited block size operations. This means that a user can enter a block size of a read or write that could be bigger than the hardware controller can handle. The hardware controller is a finite amount of space. So what we do is we break up that request into the maximum size that the hardware controller can handle and iterate through that. This means this is abstracted away from the user, and they're able to use the hardware controller in a way that they do not see the limitations that the FPGA fabric can create.
Some ongoing objectives of this project would be to implement HS200 and HS400 modes, which allow us to send a faster clock rate to the device.
We've also considered porting it over to a Linux driver. Having a full operating system would allow further expansion of the driver to include things like multiple controllers, parallel reads and writes. Concludes our presentation. Are there any questions?